We're going to look at today as multiplying functions and using dilations to create new functions. Okay, so to dilate something means you're going to change the way it is, the way it looks or how it acts, all right, by multiplying it by something called a scale factor. Now, a scale factor could be a fraction, it could be a variable, it could be a whole number, all right, and whatever you multiply it by is going to change it. Okay, so to kind of give you a visual idea of what this looks like, we're going to use it on an object. We're going to dilate this triangle, in example 1 here, by a scale factor of 3. I'm going to sketch a picture of the dilated triangle. Now, multiplying it by 3 is not going to change the fact that it's still a triangle. Okay, so we're still going to have a triangle, it's just going to be a little bit different. We're going to change its size. That's what a dilation could be. Okay, we could make it smaller or bigger. If we're multiplying it by a fraction, it would make the triangle smaller, but we're multiplying it by 3. So what we're going to do is take all the different sides of our triangle and multiply them by 3, our scale factor. So we get 9, 12, and 15. So it's still a triangle, it's just bigger. We can do the same thing with functions. Okay, we're going to dilate this function f of x equals x squared by 2 to create the new function g of x. Now, an important piece of these is you got to make sure you know what you're multiplying or what you're creating. We are creating g of x. When you write your answers, it has to be g of x. It can't be something else. You've already been told what it is. You just have to use it. Okay. So if we're going to dilate our x squared function by 2, we're going to multiply 2 times x squared. Excuse me. And that's it. We're done. Don't make this more complicated than it is. If we're dilating a function by something, you're just multiplying it there. Okay. All right, so let's look at 3. We're going to delve in a little bit more of this and see some other stuff. So the graph shows the function f of x equals x plus 3. We're going to dilate this f of x function by 3 to create a new function g of x. We're going to write this down. We have g of x, that's our new function. We're going to take our dilation of 3, we're going to put it in front, and we're going to put the other function that we're using, the f of x, in parentheses. Now, it's important that you put this in parentheses because unlike our example here, where x squared is just one term, x plus 3 is 2 terms. So when you multiply it by 3, you have to put it in parentheses because when you distribute it, it's got to go to both pieces. Okay, so that's an important piece. Now, you could have put the x squared over here in parentheses, but it wasn't necessary because there's only one term to multiply. Because you have 2 terms, you need to put it in parentheses for this question. All right, so now we're going to look at how this looks visually. Okay, so the first column you see in this table is the x values. These are the x values you get from your graph, the x-axis numbers. Okay, so we're going to pick x-axis numbers. There's no necessary right or wrong answer, but there are some better answers than others. Okay, I like to try and stick close to the origin when you're looking at x values. So I'm going to pick 2, 1, 0, -1, and 2. All right. One of the reasons I like these numbers is because, well, they're smaller as well. You're not picking 10 and -10 because then you're going to have to do probably harder math problems. So with smaller numbers, usually the math is a little bit easier. Okay, so now we're going to find out for f of x, what are the values of the points for this function. Okay, so there's a couple ways you can do this. One, you can put these values, these x values, into the f of x function, x plus 3, and figure out what it is. You can also look at the graph and find out where, if you look at 2, if you look at 2 on the x-axis, what is it for the y on the graph? You can go through that way either. It doesn't make a difference. I think using the function is going to be a little bit easier, so I'm going to use that. I put 2 in for x plus 3, so 2 plus 3 is 5, 1 plus 3 is 4, 0 plus 3 is 3. You kind of get the idea of where this is going. I'm going to fill out the rest of the numbers. Okay, so these are the points. These are points. Think of them as points that make up the line on the graph. Okay, but now we're going to make our new function g of x. So what we're going to do is we're going to take the values of the f of x, which is right here, and multiply them by 3. So we're going to take this column, 5, 4, 3, 2, 1, and multiply all those numbers by 3 to get our new values for g of x. So 3 times 5 is 15, 4 times 3 is 12, 3 times 3 is 9, 3 times 2 is 6, and 3 times 1 is 3. So now the points are going to consist of the x values and our new g of x values. So 2 comma 15 is 1 point, 1 comma 12, we'll graph the other three because they actually fit on the graph. 0 comma 9 is right here. Negative 1 comma, that's a negative 2. Negative 1 comma 6 is right, where's 5? Right there. And negative 2 comma 3 is right here. So this is our new line based off of our new points to make g of x. So this is g of x, and this is f of x. Okay. And the last question here is going to be an important question as we're moving forward with this unit. How did the dilation change the degree of the function? So if we look at the degree of the original function, the degree of the original function is the exponent on the x, which is 1. If we look at the next function, if we multiplied out 3 times x plus 3, we'd get 3x plus 9. Well, that's still a degree of 1, so the degree did not change. So there would be no change. Still linear. So it's still a linear function. Okay, but in the next one we're going to see that there is going to be a change. I'm going to show you what that looks like. So this, number 4, it says, graph shows the function k of x equals x plus 3. So notice the two functions we're dealing with from f of x and k of x are the same values, x plus 3. But in this case, we're going to dilate k of x by x to create the function m of x. So here's m of x. We're going to multiply by x to x plus 3. Oops. Okay, so it's a little different now. We're not multiplying by 3, we're multiplying by x. Okay, so the graph is still the same. We're going to still use the same x values. We're going to use negative 2, negative 1, 0. Actually, let's go back up there. 2, 1, 0, negative 1, and negative 2. Okay, so our k values will be the same as well. So we had 5, 4, 3, 2, 1. All right, but now when we're doing this, think about what we did in our function. We'd have the x value, which are these. Okay, and that gives us the k of x, but now we're going to multiply by the same values again for this x. So what we're going to do is we're going to take this term, x, and multiply by k of x to give us m of x. Because we're multiplying this function by the x value, which is there. Okay, so we have 2 times 5 is 10, 1 times 4 is 4, 0 times 3 is 0, negative 1 times 2 is negative 2, and negative 2 times positive 1 is also negative 2. Okay, so doing that is kind of the most complicated thing. All right, in the first one we just multiplied the k of x values, or the f of x values rather, by our dilation. We are doing the same thing, but because our dilation is an x, which is found on that first column, we're just multiplying our two values together to give us the third, which would be the m of x. Okay. All right, so now what we're going to do is we're going to take those values, and now we're going to use them as points. So we're using the x terms, because those are the terms on our x-axis. Or the y values are our new m of x. So we have 2 comma 10, 1 comma 4, 0 comma 0, negative 1 comma negative 2, negative 2 comma negative 2. All right, if we were to keep going, we would find more points. The graph's going to look something like this. Let's see how close I can get it. So you're going to have a point there, have a point there eventually, and then you'll have a point right here. I was pretty darn close. Okay, so now our graph looks completely different. It's no longer a line. And the reason being is, if you were to take the function that we have, I'm going to erase all this stuff here. Actually, I'm going to erase all this and rewrite it so it's clearer. We had x and x plus 3. If we redistribute the x times the x plus 3, we get x squared plus 3x. So what that's saying is, our function at the beginning, when we had it as k of x, had a degree of 1. Well, now we have a degree of 2. So the degree did change. So it went from a degree of 1 to a degree of 2. So it went from linear to a quadratic. Okay, and a quadratic has a parabola, which makes sense because that's what our new graph looks like. All right, let's look at one more example. Same idea. So we have a graph that shows the function h of x is equal to negative x minus 3. We're going to dilate that by x to create j of x. So we have j of x. We're dilating by x, and it's going to be negative x minus 3. All right, this time we don't have a table of values, but you can still make your own based on what you're given. Okay, you can either use the x values that you know you want to use, which I did up in those the tables. I used 2, 1, 0, negative 1, and 2, negative 2. All right, if you're like, well, I don't know what the values are, you can always look at the graph too. Okay, so you could say that at negative 2 we have negative 1, at negative 1 we have negative 2, at 0 we have negative 3, and so on and so forth. So those 5 points make up the same, you can make the same table we had before. Okay, so if we're going to do this, let's say we're going to have, we have our x values are negative, I'll get it, are 2, 1, 0, negative 1, and 2. All right, we can see that the values we're using are negative 5, negative 4, negative 3, negative 2, and negative 1. So when we're making our new equation, or our new function, sorry, we're going to take these values and multiply them together, because again, we're multiplying by the x. Let's go over. We're multiplying by the x. So these values here are from this second column. All right. And what we're going to do is we're going to multiply the x terms by that second column to give us the next new function. So it's going to give us negative 10, negative 4, 0, 2. I forgot to put the negative on that. That's also 2. So if we were to graph these points, so we have 2 comma negative 10. We have 1 comma negative 4. We have 0 comma 0. Negative 1 comma 2. Negative 2 comma 2. So our graph is almost the same thing as before, but now it's going to be upside down. Okay. So that would be the graph. All right, so write the equation representing the new function j of x. What is the new function family? What function family does the new function belong to? So we have j of x is equal to, now we're going to multiply it out. I'm going to give you negative x squared minus 3x. Okay, so what function family does this belong to? Because it's got a degree of 2, it is a quadratic. Okay. So that's the first part, showing you how when you dilate by something, it can change what function it is and how it looks and all the other things like that go along with it. Okay, it could also just change its size like we saw in the example 2, question 3. All right, now what we're going to do is do a little bit more, but it's actually very simple. And it's very frustrating when students do these problems and get completely confused and make it much harder than it is. So please pay attention to these 4 questions. 6 questions. I lied. All right. And we're doing so many because it is so easy that you can do this, but students make mistakes on it and think they're overthinking it all the time. All right. So let's get into it. So we're going to dilate the function f of x by a factor of x and write the new function g of x. So we're going to write g of x. We're going to multiply by a factor of x. All right, now what we're going to do is we're going to put everything else that used to be in there in parentheses, just to make sure that we can keep everything separated. So we have 3x and x minus 4. Okay, that is all you have to do to write the new function. You're putting the dilation in front and putting everything else behind it. Okay, next part, what are the zeros of the new function? This is actually very easy because what you've done when you have that new function that we just wrote is we already have this factored. So all you have to do is take the 3 different pieces that you have, that's 1, there's 2, there's 3, and set them all equal to 0. And I'll solve them. Well, here you're going to get x is equal to 0 because that's what it is. This you divide by, the second one you divide by 3. 0 divided by 3 is 0. And the last one, you add 4, so x equals 4. You're done. Okay, when it says zeros, it's saying, where does that graph cross the x-axis? That is where x equals 0, so that's why you set all the factors equal to 0. All right, the last piece is writing the function g of x in standard form. In standard form, what you have to do is you have to multiply everything together. So we're going to take our x, our 3x, and our x minus 4, and then we're going to multiply them together. Okay, so let's practice that because this causes problems. Okay, I'm going to try and show you maybe a couple different ways to do this. The first one is what we've done this before. All right, but here's where it runs into problems. When you do this, you're multiplying x times 3x, but then you're not continuing it. You're only multiplying it once, not by everything multiple times. So 3x times x is going to be 3x squared. Excuse me. We still have x minus 4 left over. Okay, but now we're going to take the 3x squared, and now we're going to distribute it to both parts in there. So we're going to get 3x to the third minus 12x squared. Okay, and this is what g of x is multiplied out in standard form. So that would be your answer. Okay. All right, number 7. We're going to take our function f of x, we're going to multiply it by, we're going to dilate it by a factor of x. So we're going to have g of x is equal to x times x plus 5. That's it. That is our new function. There's nothing else you have to do to write the new function. Don't multiply it out unless it asks you to. Okay. All right, next, what are the zeros? You take our factors. So the x and the x plus 5. You set them both equal to 0 and solve them for x. So x will equal 0 and x will equal negative 5. That is it. All right. When it says write the function g of x in standard form, now you have to multiply it out. So x and x plus 5. Now we're going to multiply this through x squared plus 5x and put the g of x out in front. And now it's in standard form. All right. Number 8. We have the function h of x equals 9x minus 1. We're going to dilate it by a factor of x plus 3. So we have j of x equals our scale factor of x plus 3. We're going to leave this in parentheses. We're going to multiply it by our original function, 9x minus 1. Okay, that's all you have to do. You have now made a new function called j of x. There's no need to multiply it again unless it asks you to. Okay, what are the zeros of this new function? We have x plus 3. We have 9x minus 1. We're going to set them both equal to 0. So the first one we subtract 3 from both sides, so we get x equals negative 3. And the second one we add 1 and divide it by 9, so x equals 1 over 9. So those are our two zeros, which are the solutions, which are also the x-intercepts. Okay, all those things mean the same thing. All right, write the function j of x in standard form. Now we're going to have to multiply it out. We have x plus 3. We have 9x minus 1. Okay, so now we can do the rainbow method if we want. We have x times 9x is 9x squared. X times negative 1 is negative x. 3 times 9x is 27x. Let's get that wrong. And 3 times negative 1 is negative 3. We're going to combine the terms that we can. 9x squared stays. Negative x plus 27x gives us plus 26x minus 3. I'm going to write down j of x in front of it. And you've now multiplied out and put it in standard form, the j of x function. Okay. All right, now it gets a little more complicated because now we're going to get into more complicated functions for some of these other ones. And we're going to show you a trick to help you out. Okay, and it helps out some students, other students don't need it. Whatever works for you is what we want you to do. Okay, so we're going to dilate our function. We're going to make a new one of m of x. We're going to dilate it by x plus 2, which we're going to put in parentheses. And here's our other function, the k of x function that we originally were given, 3x plus 1, and x minus 7. Okay, that is the function. There's no it's not necessary to do anything else. Okay. What are the zeros of the function? Again, we take our factors. We do x plus 2. Oops, I didn't do the parentheses. Set equal to 0. We have 3x plus 1. Set equal to 0. We have x minus 7. Set equal to 0. Okay, so all we're doing is, again, we're taking the factors, setting them all equal to 0, and solving them for x. So the first one, we're going to subtract 2, which gives you negative 2. The next one, you subtract 1 and divide by 3, so negative 1/3. The last one, we're going to add 7, so positive 7. These are our zeros. Okay, that's all we have to do. We don't actually have to write them as points. We're just solving them for x. All right, now writing this in standard form. So this is where it kind of gets a little more complicated, because now we have 3 terms that are 2 terms apiece. Okay. So here's a different way to do these problems as far as multiplying in standard form. Now you can still do the rainbow method, and I'm going to show you that in, like, let's say number 10, but I'm going to do this other method to help you organize your information. It might help out some of you students. So there is like a box method to do these things. So we're going to put 2 of the functions together, x plus 2, and we're going to have 3x and 1. Okay, so what we're going to do is we're going to multiply the numbers that correspond to the boxes. So x times 3x is 3x squared. 3x times 2 is 6x. X times 1 is x. And 1 times 2 is 2. Okay, so this helps organize. So all the stuff that you had, that you multiplied together, you can combine to make like terms if you have. So we have 3x squared. The 6x and the x can be combined to give you 7x, and then plus 2 on the end. So what we've done is we've multiplied 2 things. Now you could get the same answer if you'd done the rainbow method. Okay, so if that works better for you, that's fine. All right, but one of the reasons we like to do this is because the next step is we still have to multiply by x minus 7. We haven't done that part yet. So what we can do is we can do the same thing we just did, but now we're going to have x and negative 7, and now we're going to do the same boxes. Because we're going to have more terms. So 3x squared times x is 3x to the third. 7x times x is 7x squared. X times 2 is going to be 2x. Negative 7 times 3x squared is negative 21x squared. Negative 7 times positive 7 is negative 49x. Negative 7 times 2 is negative 14. Okay, again, you're going to see that the ones that are diagonally across from each other are the like terms that we're going to combine. Okay, so we have 3x cubed. So we have negative 21 plus 7. It's going to give you negative 14x squared. We have negative 49 plus 2 is going to give you negative 47x. And negative 14 is left over. So now we have m of x, oops, that's not an m, equals this. Okay, so some students like this little box method to help organize their information when they're multiplying things. If that helps you, awesome, use it. Excuse me. If you don't need it, then don't use it. Okay? All right, we're going to show you how to do the rainbow method in the next question, and then we're going to go back to the boxes in the last one. Okay? The reason we're doing so many of these is because in last year's tests, these are the questions that people were getting wrong, and we want to make sure you understand how to do it. Okay? So given the function f of x, there is our function. We're going to dilate it by x minus 6 to make k of x. So we have our dilation, x minus 6, and we have our original function. So 5x minus 1 and 2x plus 5. Our zeros, x minus 6, 5x minus 1, and 2x plus 5, setting all of them equal to 0. And then solving. X equals, we're going to add 6. Next one, we're going to add 1 and divide by 5. The next one, we're going to subtract 5 and divide by 2. Now writing it in standard form. So like as I said, we're going to use this one. We're going to use the rainbow method. So we can see everything. And again, pick whichever method works best for you. So here we have x times 5x, which is 5x squared. X times negative 1, which is negative x. Negative 6 times 5, which is negative 30x. And negative 6 times negative 1, which is positive 6. We combine our like terms. Okay, next we got to do the other one. So we have, I'm going to do it over here. We have 2x plus 5. Actually, you know what, I'm going to write it down further. And we're going to multiply that by, we just multiplied, which is 5x squared minus 31x plus 6. Okay, so we're going to do 2x times 5x squared. We're going to do 2x times negative 31x. And 2x times 6. On the other side, we're going to do positive 5 times 5x squared. I'm going to put that, oh, this should be squared. I'm going to have 25x squared. I'm going to line them up. Oh, I'm making mistakes here. I forgot the x's in there. My apologies. 5 times negative 31 is going to be negative 155x. And 5 times 6 is going to be positive 30. Excuse me. Now I combine the like terms. I'm going to get 10x cubed. I got 62 gives you negative 37x squared. And this is negative 143x plus 30. Oh, I've got to label it. This is k of x. There you go. Now that seemed like a little bit more work maybe. I don't know. Not sure. It's probably about the same. But it just shows you different ways to do the problem. I forgot the little rainbow over there. Okay, same idea, just different method of getting there. Either one works. I don't care which one you use. All right, last one, we're going to use the box method again to help show you out how these work. So you have k of x is equal to our dilation as x. Then we have x plus 1 and 2x minus 5. 0 is the new function, r. X equals 0, x plus 1 equals 0, and 2x minus 5 equals 0. So if you solve them, this one's already done. We're going to subtract 1. We're going to add 5 and divide by 2. For writing it in standard form, all right, we have x times x plus 1. All right, I can just do that really quickly as x squared plus 1x. Then I'm going to use the box for the other one just to show you guys again how it works. We have 2x and minus 5. So x squared times 2x is 2x to the third. That's bigger. 2x times x is 2x squared. X squared times negative 5 is negative 5x squared. Negative 5 times x is negative 5x. So I write out the pieces that we have. I can combine the like terms here to give you negative 3x squared minus 5x. I'm going to put the k of x out in front. And there we go. All right, so that's been a bunch of different examples to help you out. So you can rewatch the video, pause it, whatever you need to do to help you out. Try the practice. The practice is going to be really important so you guys can do these on your own and make sure you know how to do it.